Hello everybody, my name is Misty and today we're going to do a deep dive into the Phobos kernel. Last time we looked at the bootloader, how we get from BIOS into 64-bit long mode. Today we're picking up right where that left off. The bootloader just handed us control, we're in 64-bit long mode and we need to actually build an operating system. So let's get into it. So, this is kernel.assembly, this is the first thing that runs after the bootloader. And yeah, it's pretty simple. We just write the letter K standing for kernel 4 times because when we're in 64-bit we have enough room to write 4 characters at the same time with color. So when I was testing, I just wanted to see if we could do this to check if it was in 64-bit mode. Should probably delete this now, but it works, okay? And this won't actually do anything now because this was when we was in VGA mode, which is when you could just put letters to the screen without having to worry about fonts and pixels. But either way, this is from old tests. This is the first thing that runs. This is the actual line that does things. So this just loads the kernel.c file, which is, I can never find anything here. This is really annoying. Should probably fix my file structure, but it's alright. So this is literally everything. This starts at kernel main. And the first thing we do is print this with VGA mode. Obviously, again, this doesn't work because we're not in VGA mode anymore. Because I've done since I've wrote this, we've done a lot of changing. Now we handle pixels, we handle things like that. We don't really do VGA stuff. Either way, this used to work. Yeah. So, this is where it gets real now. The kernel has to initialize everything in the right order, and that matters a lot. So let's walk through each steps. So, paging init. This sets up our page tables so we have virtual memory. Without this, we're just running on whatever page tables the bootloader left us, which is, not the best. So, let's open paging.c. Here we have all of the defined page tables. So this is how x86-64 paging works. You've got 4 levels of page tables: PML4, PDPT, PD, and PT, as we can see here. Each one is a 512 entry table, and each entry is 8 bytes. These are all page aligned in the kernel's BSS section. So let's go to paging init. Right. This is where we build the identity map. We're mapping the first 64 megabytes of physical memory. This means virtual address equals physical address. Super important for a kernel because hardware addresses like the frame buffer, which is to do with rendering, need to just work. So, 2 sets of flags here. Supervisor only and user accessible. Below 1 megabyte is kernel territory. That's where our kernel code lives. VGA memory, BIOS stuff. Above 1 meg, we mark pages as user accessible so our user programs can use that memory later. So, this is the mapping loop here, down here. So, this double loop maps all 64 megabytes. For each 2 megabyte region, that's 1 PD entry, we fill in all 512 page table entries. Each entry maps a 4 kilobyte page. The math, page directory index times 2 megabytes plus page table index times 4 kilobytes gives you the physical address. That might sound complicated, but it's right. So, lines 54. This is cool. Page 0 is special. We mark it supervisor only, even though it's below 1 megabyte. This gives us null pointer protection in user mode. If a user program dereferences a null pointer, which happens a lot, it page faults instead of reading garbage. Classic operating system trick. If we didn't have this, if any user mode code dereferenced the null pointer, blows up the whole OS. This simple fix. So, protecting page table pages. So, we don't want user code to be able to modify the page tables. That would be a massive security hole. So we strip the user bit from those specific pages. Here we just have some bitwise operations to strip that bit. And yeah, so let's look at line 78. This is where we load our new PML4 address into the CR3 register. The CPU immediately starts using our page tables. If we got anything wrong, this is where we triple fault and reboot. So if anything wrong happened here, which in testing, trust me, a lot of things wrong happened, it triple faults, reboots, everything blows up. This wasn't fun to develop, but we move on. So let's go back into kernel.c. If I can find it, there we go. Let's look at line 80. So, PMM init. This is the physical memory manager. We're telling it, hey, usable RAM starts at 2 megabytes and goes up to 64 megabytes. Everything below 2 megabytes is reserved for the kernel. So, let's open pmm.c. I think I can just go to definition. Yep. PMM init. So, the first bit of the file, the PMM is a bitmap allocator, dead simple. Line 8 is just one big bitmap array. Each bit represents one 4 kilobyte page. Bit set means allocated, bit clear means free. The helpers on line 12 to 14, set bit, clear bit, test bit, just do bitwise operations on 64-bit integers. So what we're doing here is called bit packing. So to maximize space, to maximize RAM space and memory space, we just pack all info into one long integer, and we just, each different bit means a separate thing. It's called bit packing. So PMM init. This aligns the start and end addresses of page boundaries, calculates how many pages we can manage, and zeroes out the bitmap. All zeros means free, ready to allocate. Cool. Let's look at PMM allocate pages. God, I can't speak. Here's the allocator. Line 42. It's a first fit scanner. Walks the bitmap looking for n contiguous free bits. When it finds them, marks them all as used, and returns a physical address. Not the fastest allocator in the world, but you know, it does the job. We don't need insane speed. So line 46. Notice the IRQ save disable. We disable interrupts before touching the bitmap. This is critical because the timer interrupt could fire mid-allocation, preempt us, and another task could try and allocate the same page. Classic concurrency bug. We save the flags and restore them after so we don't accidentally leave interrupts disabled. So let's go back to kernel.c. Let's go to lines 82 to 97. So this is where we do the frame buffer stuff. This is to do with rendering. So the bootloader already set up a VESA video mode, which is 1024 by 768 at 32 bits per pixel, if I'm not wrong. And the frame buffer address was stashed at a known location. In this case, it's 0x5028. We read it, calculate the total size in bytes, and identity map every page of the frame buffer into our page tables. So, line 94, window init, sets up the window management system. Line 95, console init, gives us a text console we can write to. And line 97, we mark the VGA text buffer at 0xB8000 as user accessible, so user task can write debug output there. This doesn't really make sense for now because we don't use VGA anymore. As you can see, this is like a temporary thing, but either way, it's still there. Some artifacts from old tests. So line 100, GDT init, the global descriptor table. In long mode, segmentation is mostly dead, but you still need the GDT for two things: defining privilege levels and the TSS. So let's open up gdt.c. Cool. These are comments that describe the GDT selectors. So, I know I've said so a lot this video, but it is what it is. So, here's the layout. 5 segments plus a TSS. Null, makes sense. Kernel code, ring 0. Then we have kernel data, ring 0 data. User data, and user code. And it has to be in this specific order because of how sysret works. It assumes user code and data are at specific offsets. Again, it's just something that like modern architecture is just expecting from... It's just a standard in the industry. Can't really change that. So, let's scroll down a bit to GDT init. Here. First, we zero out the TSS, as we can see. That's the task state segment. The TSS is how the CPU knows where to find the kernel stack when transitioning from user mode to kernel mode. Line 92, we set the IOPB offset. Cool. Then we have the actual entries. We set up each GDT entry. The important bits are the access bytes. 0x9a for kernel code means present. DPL0 executable. 0xFA for user code means present. DPL3 and executable. DPL is the privilege level. 0 is the kernel. 3 is user. Cool. Then lines 121 down to 139. So this is assembly. This is the scary part. We load the GDT with LGDT. Load GDT, then immediately reload all segment registers. DS, ES, SS, all get 0x10 kernel data. And then we do a far return to reload CS with 0x08. And if you don't reload CS after loading a new GDT, you're running with stale segment state and weird things happen. So, this is where we load the TSS. We load it with LTR. Selects 0x28, points to our TSS entry. Now when a user program does a syscall or an interrupt fires while in user mode, the CPU knows to switch from RSP0 from the TSS. So, this is the little function here. TSS set RSP0 gets called every time we context switch to a different process. Each process has its own kernel stack and we need to update the TSS so the CPU switches to the right one. Back to kernel.c. I know this is going to be a long video and we're going line by line here, but a lot of you wanted some in-depth tutorials, so we're going to give it to you. So line 101, CPU enable FPU SSE. So this was actually needed specifically for Doom, which in general this is for floating points. But for Doom, we didn't actually have floats until we ported Doom over, and then I realized we needed floats, so we had to enable this. So we clear the EM and TS bits in CR0. Those would trap on FPU instructions. Set MP so wait fwait works. Then enable 0s fxsr and osx mme in CR4 for SSE support. Finally, fn init to reset the FPU state. Without this, any floating point instruction would crash. Cool. Lines 103 to 108. The scheduler setup. Schedule init initializes the task array. Then schedule bootstrap current wraps the currently running kernel thread as task 1, so the scheduler can manage it. TTY init sets up the terminal, foreground process groups, and all of that. Cool. So let's look at schedule.c. Lines 23. It's a big file. Lines 23 to 31. So this is just these. Here's the scheduler state. An array of 16 tasks. Max tasks is 16, which is, kind of Should probably change that, because that will hit a hard limitation as soon as this OS starts becoming bigger. But either way, a circular linked list, that's hard to say, run queue, a pointer to the current task, and some state flags. Task ID start at 1. Simple stuff. So let's look at scheduling it. I've got visual mode on. Scheduling it. Here we are. So this just zeroes everything out. Every task start as unused. So schedule bootstrap current, which is a bit further down. Here we are. This is a clever trick. We're already running code right now in kernel main. So we allocate a task struct. Here we are. Give it to the kernel's page tables, CR3, and then say this is the current task. Now the scheduler can preempt us like any other task. And that is a lot of the kernel. There's way more, but I don't have time to put it all in one video. This video is already getting quite long. So we're going to leave it here. Make sure you like and comment if you want another video, maybe part 2 to the kernel. And I'm happy to dive even deeper if you lot want. And yeah, thanks for watching. Hope you guys enjoyed. Peace.